Monika Nitsche, who's going to talk about incompressible viscous flow, vortex shedding, and low-order models.
Thank you. And thank you for the organizers. It's been a pleasure to be here. It's been a wonderful experience, so thanks for inviting me. This talk is going to be along different lines than previous talks, so I hope I can get you interested in it anyways. I did feel like I had to preface it by saying this is incompressible viscous flow. I'm interested in vortex shedding and approximating, but I'm interested in the shedding in its own sake, as well as the comparison with low-order models for it. And this work is together with Ling Xu, who's a former student who is now at Georgia State. She's done a tremendous job in this work. So, all right, let's see if this works. This being a school, I will give quite a bit of background. Some of it you've seen several times before. Then I want to talk about, so the background is mostly on vortex sheets, and then I want to talk about the separation, boundary layer separation, and the vortex sheet approximation for it. And then the problem I'm ultimately interested in is this, whoopsie. My test case to understand separation is this very simple flow past a plate. So in this case, the flow goes from bottom to top. You get boundary layers of vorticity forming, and they separate, forming a counter-rotating pair of vortices. So that's my test case. And I'm actually looking at accelerated fluid velocity. You can think of this as the plate moving down or the background flow moving upwards. It's just a change of reference, which doesn't change the vorticity. It does change, the change of reference frame does change the forces acting on the plate, but not the vorticity and velocity in the streaklines that I will be showing here. So I'll spend quite a bit of time on impulsively started flow, then accelerated flows, and the main goals are, again, learn about the flow dynamics itself. I mean, this is such a basic flow, but there's relatively little detail on the early starting flow in particular for this very simple flow in the literature. So that's one of the goals, is to just learn more about the flow. And then the vortex sheet models are based on approximating the shed circulation. So I'm in particular interested in computing circulation for this viscous flow, so I have a reference to compare with. And again, that's something that has not been computed in the literature with the detail at early times as we're doing it here. And then study the dependence of the solution on viscosity, as well as getting some benchmark results to compare with the low-order models. And then I'll show a little bit of a comparison at the end. All right, so the background, my velocity is u. The vorticity is the curl of the velocity. It has 3 non-zero components in general in 3D. The velocity is a vector. If the velocity is smooth, then it has a rotational component. If the vorticity is smooth, there is a rotational component of the velocity around it. 2D flow refers to invariance in the z direction and zero velocity in the z direction. And with that, the vorticity has only one non-zero component, denoted by the scalar vorticity, which I'm also going to call omega, because I haven't figured out how to do a bold omega in LaTeX. If you know how to do it, let me know. An axisymmetric flow. So the vortex vector is points up out of the xy plane and is usually denoted by a point in the xy plane. But what you really, if you see that point, you really should be thinking of a vortex line pointing out at you. An axisymmetric flow, which means invariance in the theta direction. You can have swirling flows, so velocity in the theta direction or not. If you don't have swirl, this is what the picture is. The vorticity vector points out of the xy plane, and the vortex filaments are circular lines. With swirl, the vortex filaments are helical. And what I'm talking about applies to both planar and axisymmetric flows, extending it without swirl. Extending it to swirl or to 3D is a lot harder. So, sample vortical flows. You have a rotating flow on the left, shear flow on the right. How do I know that there's vorticity, the circulation? There's obvious circulation going around this curve. By Stokes, I know that there's got to be some vorticity inside there, as well as over here. I know there's circulation, there's flow along the tangential direction. So there's a positive component in the tangential direction up here, a positive component in the tangential over here. There's actually zero component in the tangential direction on the side, so there's a total flux around the curve. That implies some vorticity, but I don't see the rotating flow because the velocity is actually a superposition of a rotation and a strain field in this case. I'm used to using one of these. So sample rotating flows are a single point vortex that corresponds to a delta function of the vorticity. The velocities field is given, in Cartesian coordinates. Over here, it's convenient to write it for these vortex sheet applications, to write it in complex form. So if you have a point with circulation gamma, the complex velocity is gamma over 2 pi I z. And the velocity decays like 1 over r. If you have a sum of point vortices, I'm going to take this for granted, my point vortex my point vortex motion, where I just sum over all the point vortices and I exclude the self-induced contribution. By Kelvin's, I know that the circulation stays constant, and an example is a counter-rotating vortex pair, which is really what I'm getting above my plate. I have two vortices, counter-rotating vortices. So I should have showed it going up because that's more related to my particular problem. In terms of shear flows, this is a sample shear flow. So what they've done over here is they have a tank with a heavy fluid in the bottom that's light, a light fluid on top that's dark. They tilt the tank, the heavy goes down, the light goes up, and that creates a shear, and it rolls up because of Hamilton stability of this flow into this well-known picture from Van Dyck's album of fluid motion. So the vortex sheet is a model for a shear layer in which the region, so this is my shear layer. I have a jump in the velocity across a region of finite thickness, or across a layer of finite thickness. There is a smooth transition of the velocity across here. There's vorticity inside of this layer. There's zero vorticity outside. The vortex sheet is a model in which the layer is approximated by a surface. The vorticity is a delta function on the surface. It's zero outside. The velocity, the tangential velocity component, has a jump across this surface. So in this picture, this vortex sheet, if this were the velocity field, then things would just, not much would happen. Okay, the velocity would, nothing is moving the sheet. I have a jump in the velocity and the tangential components across it, but nothing is moving the sheet. In general, you have the sheet moves in the normal direction. So there is, on top of a tangential discontinuity, there is a normal velocity component that is continuous across the sheet. So the tangential velocity is discontinuous. The normal velocity is discontinuous across the sheet. The sheet is parametrized by a parameter. One of the possible parameterization is parameterized by a parameter gamma that changes along the sheet, and I want gamma to be a circulation parameter. So what that means is if I have a point that's parameterized by gamma equal to 0, and I have another one that's parameterized by gamma equal to star, the gamma star happens to be exactly the circulation contained in this curve. So I can do that at time 0. And I would like, so I'm going to move this sheet, and this point that starts out at gamma 0 times 0 moves to this point over here, gamma 0 times t. This point, gamma star times 0, moves to gamma star times t at time t. And I would like to say, I would like gamma to remain being the integral vorticity between the particle at gamma 0 and gamma and the particle at gamma star at all times. I can certainly do that at time 0, but I would like this to be true at all times. So I would like to apply Kelvin's theorem and say, okay, a circulation around a curve that moves from here to there is conserved. So therefore, this quantity does not change in time. The circulation does not change in time, and it's what we call a Lagrangian parameter. The problem with that argument is that the velocity of these points is not well defined. The normal velocity is well defined, but the tangential velocity is not well defined, because I can move these points in the tangential direction with any velocity I want. I still get the same position of the sheet at a later time. So the velocity in the tangential direction is not defined. And we actually take advantage of this freedom in certain situations where we move the points in the tangential velocity so as to bunch up at a point of choice, for example. But over here, I want them to move exactly so that my circulation is conserved. And that is true if you move them with the Birkhoff-Rod equations. And that is not a trivial thing to show as far as but if you move them with the Birkhoff-Rod equations, which are written this way as a Hilbert transform, one can show, because of the Plemmel equations, that this is exactly the average of the fluid velocity. And if the points move with this velocity, then the circulation is conserved. Okay, so that's, I'll move them with this. This is all 2D, but it's easily to extend it to 3D. I'll move them with this velocity. And then, and this is a principal value integral, because this function is actually not integrable. But in the principal value sense, this is the average of the velocities above and below. So the point vortex approximation refers to discretizing these equations by taking your sheet, approximating it by a discrete number of point vortices. They have to be equally spaced in gamma, so that you can approximate the principal value integral by ignoring the contribution of itself, of the point itself. Okay, so this, if the points are equally spaced, this approximation approximates the principal value integral. So you have a set of ODEs for the points, and you say, okay, I'm done. I can go and compute the motion. But there is one more thing that is important for what I do to understand about vortex sheets, and it's the vortex sheet strength. Okay, so if I look at my curve, okay, and this curve has a tangential discontinuity. It has a discontinuity in the tangential velocity. It has a normal velocity which is continuous across this sheet. And I want to compute the circulation around the little piece of that sheet. So I'm going to call this delta gamma. So it's the circulation around that little piece. In this region below, which I'm calling the velocity is u minus over here, the contribution, if this is very small, I can assume the velocity is constant. So the contribution from below is u minus times delta s. From above, the component of u dot t is minus u plus. So I get, from above, I get the contribution of minus u plus delta s. So I get that delta gamma is the negative jump in the velocity times delta s. And if you divide by delta s, you get that this is approximately the jump. You take a limit, and you get that the derivative of gamma with respect to s is the jump in the negative jump in the velocity. I should put a negative sign in here, right? I did mess up over here. It's a negative sign. And that's what we call the vortex sheet strength. So what is really important to know is that if you have a distribution, if you have a sheet given circulation distribution gamma of x or gamma of s, or if you know the circulation distribution on your sheet, then you know the jump in the velocity across, and you know the average velocity of the sheet. Okay. Similarly, if you know the jump, and then you know the gamma ds, then you know gamma, and then you know the average velocity. So if you can figure out the jump and the velocity, then you really have the whole thing. Okay, so the problem is the Hamilton instability of this. So if you take these, they're called the Birkhoff-Rod equations, the ones I just had written down. You do a linear stability analysis. You take a small perturbation of a flat sheet. So z equals gamma. That means the x component is gamma, because there's no imaginary component, and the y component is 0. So that's the flat sheet. This is the flat sheet. Maybe I should take my little arrow out of there. And you take a small perturbation of that, of a perturbation of this particular form. So you linearize the equations around gamma. And you look for a solution of this form. So it grows like e to the omega t, and it has wave number k. Then you substitute it into the linearized equation, and you get the dispersion relation, which is of this form, omega equals plus or minus k. That means that for any wave number, you have a growing and decaying mode. But more importantly, the higher the wave number is, so the shorter your wave is, the faster the growth rate. And that's the definition of being ill-posed in the sense of Hadamard. And that's actually what causes you numerical problems as well as, so there's two problems. So first of all, so this is the dispersion relationship for the vortex sheet. As k increases, this is the growing mode. The perturbations grow like e to the omega t, where omega is increases as k increases. Whereas for a shear layer, you can do a similar analysis, and you have a growing mode in force AK that grows the most, whereas the other ones are damped. And that's the growing mode that you actually see in these experiments. So the problem that this causes numerically is that you're trying to compute to approximate your sheet by a finite number of points. And you want to get better and better approximation the more points you use. The more points you use, round off introduces wave numbers that are that are increasingly large the more points you use. So as you increase the number of points that you use to discretize your sheet, you're introducing larger modes at the level of round-off error, but they grow very large, and that introduces noise. And one way to handle that is the Krasny filter, which is the reason this is significant is because before Krasny's work, people have been trying to compute vortex sheet motions, and they were getting nothing that really made a lot of sense, and they couldn't explain why it wasn't working, and they were basically dismissing the model. And only after this understanding that came from this work do we know what's going on. So if you apply a filter that precisely cancels the modes introduced by round-off error, you can control the problem. So that's the first problem. The second problem is that if singularity forms in finite time, and the point vortex approximation does not converge past that time, which requires one to regularize the motion. So this is what results look like actually very near the critical time. Using the filtered point vortex approximation, so you actually don't have any noise if you filter these. And it's known, and there are several people that have been involved, that show that the singularity in the vortex sheet looks like C of gamma looks like gamma to the 3/2. That means the slope is continuous, but the curvature is unbounded. And in this case, it happens in this particular initial condition. It happens right over here. So before this time, everything is nice about vortex sheets. You can show convergence of the point vortex approximation, of the filtered point vortex approximation, and that's the work by Kavlish, Ercolani, Hauer, and Nundes. And Cowley, Baker, and Navier showed that the singularity is generic for 2D and 3D. And Moore is one of the first ones that get an indication using asymptotics of this type of singularity. So before the singularity forms, you know that the point vortex method converges, and you know how to compute it using the filter. But afterwards, the point vortex approximation does not converge, and the approach taken is to regularize it somehow. And over here, I've regularized the motion by introducing a small parameter, delta squared, in the denominator. And that, I mean, this function is now integrable. I don't need a principal value integral. I can discretize this, and one can show that solutions to these equations exist for all times. And once you compute the equations with the regularized velocity, you can compute to all times the solution rolls up after the singularity has formed. Now, there are other ways of regularizing the motion. This regularization corresponds to taking the kernel, use of our kernel and convolving it with an algebraically decaying smooth function. That's what this kernel is. You can also convolve it with an exponentially decaying smooth function. That's another regularization. A third one is the Euler alpha regularization. In none of those cases is really much known about the limit. It is known that the limit is a weak solution to the Euler equations, but it's not known whether there's any pointwise, if it converges. Pointwise, what the limit is, whether the limit depends, if it exists, in a strong sense, whether it depends on the regularization, and how it compares with the viscous. In the real flow, the viscosity is the regularizing mechanism, and you can think of viscosity going to zero and how this limit compares with. So that's one of the big, after all this years, this is still one of the big open questions. Okay, and the Euler alpha actually is in my mind, one of the nicest regularizations. It is harder to compute. It takes more time to compute, but it is the least regularizing, yet it's still sufficiently regularizing to let you compute past the singularity formation. So it is a really nice way to regularize them. Okay. Now, what I'm doing, I need to understand a little bit about self-similar roll-up. So this problem has been considered as far back as Cardan's work. They considered a semi-infinite sheet, so that's what this dashed line is. A semi-infinite sheet that induces flow past a semi-infinite plate, okay? And that flow, potential flow, what that potential flow looks like from potential flow. So you know what the jump in velocity is across you, so you know the sheet strength. So you know exactly what the initial condition is, what the sheet is that induces potential flow past here. And then you take that sheet and you let it go. And you let it go and it rolls up like this. And these are the governing equations. This is your initial condition. This is the gamma that you get from your potential solution. By looking at the jump in the velocity across, that's exactly this. These are the Birkhoff-Rod equations. If you take this equation and replace z by z over L and t by t over capital T, as long as you let L be the same as capital T to the 2/3, you get exactly the same equation. So what that means is that your solution at time z, at time t, at time, and position z is the same as the solution at time t prime and z prime, as long as z prime, t prime look like that. Okay, and that gives you a self-similar shape of the roll-up that was first found by Cardan. And it tells you, for example, that the center of this moves is proportional to t to the 2/3. And it tells you that the circulation that rolls up is proportional to t to the 1/3. So there's some scaling laws that you can deduce from this. And Moore found some higher order corrections to the self-similar spiral. And Pullen computed the spiral by just trying to find a solution to the self-similar equation. So eliminated time, and then he just tried to find a solution to the self-similar equation. So this is not something that has evolved dynamically, but this is a solution to the self-similar equations. And it's not known that whether this is stable or not. And when you compute the vortex sheet solutions, the regularized sheet solutions, they appear to converge to this up to some point. So it is not clear that they actually they appear to converge to this for some range of deltas, and then something funny happens, and you can't compute with smaller values of delta. So it's not known whether that solution, the regularized vortex sheet solutions, actually converge to this self-similar spiral. Okay, so that goes together with all those open questions. But I'm going to use the regularized vortex sheet motion to compute separation. Okay, so now I want to talk about separation. So the Euler equations, first order set of equations with a boundary condition that there is no flow going into the wall. So one of the velocity components is 0. So this parallel flow past the wall is the solution of the Euler equations. Okay. Whereas in Navier-Stokes equations, I have a second order derivative showing up over here in the diffusion. I need a second boundary condition, and the correct boundary condition is that the second component of velocity is also 0. So for the Navier-Stokes equations, your velocity must be 0 at the wall if the wall doesn't move. Otherwise, it must move with the wall velocity. So if you have parallel flow near the wall, that creates a transition layer in which your vorticity gradients are large. Vorticity is Vx minus Uy. Over here, I have no V because I've plotted this parallel flow. But the Uy is actually very large in here. The Uy is 0 over there, but it's very large in here. So I have a region of large vorticity forming near the wall, and that's one of the main mechanisms by which bound vorticity is created in the flow. And then if you have a corner, that vorticity layer can separate and move into the flow, and that's what I'm referring to as a separated flow. There's an example. I mean, you may have seen this, but I think it's a really cool picture of a separated flow. So you have flow going around the wing. You also have, so around the tip over here, and you also have flow going around this way. So what you get is you have a whole sheet or a shear layer of vorticity, and it rolls up all the way around in the form of a horseshoe. So you really have a horseshoe vortex, but I'm only seeing the one, the roll-up of the two sides of this long sheet of vorticity that has separated. So this is that trailing vortex that you see when you look up at the sky and you see two trailing vortices behind the plane. That's visualized over here near the ground. And what we do see in the sky is, so your velocities, I mean, you have a vortex over here. Your velocity is very large in the middle. By Bernoulli, the pressure is very small in the middle, so you have condensation. So what you're actually seeing is water, is a little cloud. It's water condensing, so it's not exhaustive or anything like that. All right, so this is one example, and it's actually related to the flow that I'm looking at, which is the flow around a plate. Some other, I mean, biolocomotion is a big area that people are interested in. This is the vorticity induced by a flapping dragonfly wing, computed by Jane Wang at Cornell. Jellyfish, I mean, this is a two-dimensional jellyfish. Making them axisymmetric is actually fairly straightforward. I mean, they've been of interest in simulations because they're self-contained, they're small. I mean, they're fairly simple. In the lab, it's easy to get a lot of jellyfish. I think they actually don't survive that easily, but it's fairly, I mean, you can have a lot of jellyfish in your lab to do experiments, and they actually contribute to circulation in the ocean, so that's one of the questions on how much they contribute to the oxygenation of the ocean. So anyways, and they're growing wildly. Anyway, so this is another example. Vortex ring, this is an axisymmetric flow. I have a tube. This is an experiment done by Didden. It has a big tank full of water, a tube in the water, so there's water everywhere. And he pushes with a piston. He pushes water out of there. That creates this flow, but they have boundary layers of vorticity along the wall. That boundary layer separates at the edge and forms a vortex ring, like you would blow, if you know how to blow a smoke ring, that's the way you form a smoke ring. And these are visualizations. So he did these nice flow visualizations, and he's also measured velocity fields and vorticity fields and circulations. Okay, this is with the accuracy available at that time. Okay, so that's a problem that I'm going to get back to. And this is a problem that we've looked at together with Kai Schneider and Eva Kanzel, related to biolocomotion. Okay, Eva is interested in the motion of moving fish, and this is sort of a very, very crude little fish. Okay, it's a plate hinged at one end, and the motion is prescribed. It oscillates and it has a background velocity coming onto it. And this is a simulation by Kai Schneider's group using the penalized Navier-Stokes method of the vortices that shed at the edge of the plate. And, all right. So we're going to model these separated flows by, so in the real flow, I have these boundary layers of vorticity in here, and they separate, and there's still, this is a shear layer separating. Okay, I should have made a big broad batch of red over here, but this is a big fat shear layer that rolls up, and I'm going to model the boundary layer by a vortex sheet, and this sheet is such that the strength of this sheet is exactly so that no flow goes through the wall, and that uniquely determines the sheet strength, and that's my bound vortex sheet. And for that, I have to set delta equal to 0 because it doesn't move. And if I set it positive, then I can't invert the linear system. I mean, it's not a well-posed system anymore. And the separated shear layer is simulated by a free vortex sheet. And for that, I do need to regularize that motion. The vortex shedding is, so in practice, at every time step, I release a little particle into the flow, and I release it parallel to the wall with the average velocity. Since I have the wall sheet strength, I know the average velocity, so I know what velocity to give it, and I know which direction, I know what speed to give it, and I know the direction, but I need to know what circulation to give it, and that's the part that I need to implement what's called the cutter condition. And for simplicity over here, I'm just going to assume the flow is in the vertical, in the horizontal direction only. I mean, if the plate is horizontal, then your velocity is going to be horizontal at the tip. So I want to compute the derivative of this, and I just worked out the details over here. I move there is a region omega which defines the circulation. You move the derivative time derivative inside. You apply the Euler equations, which say that partial t is minus u dot grad omega. And then you can write that because we're an incompressible flow, this is the same as the divergence of omega u. Then I apply the divergence theorem, and I write it as an integral over, oops, something happened. These should have been omegas over here. Okay, this is an omega, this is an omega, this is an omega until I take the divergence theorem. Sorry. I'll fix it before I pass on my PDFs. And so I'm taking omega times u dot n, and the vorticity is a delta function across here. Oh, the vorticity is Vx minus Uy, but it's parallel, so it's minus Uy. U dot n, because it's parallel, is just U. So this is the derivative of U squared, 1/2 the derivative of U squared, and I can take the antiderivative of that, and I get that the gamma dt is 1/2 u minus squared minus u plus squared. And then I have, if by any chance u plus were in this direction, u minus were in the opposite direction, or u minus were exactly the same magnitude, then this is 0. If it is in the opposite direction, I set it equal to 0. If one of these does not move away from the plate, I set it equal to 0. And that's a little mechanism that maybe seems artificial, but it doesn't affect the solution at all. The details of how you implement this, somehow you just have to get the motion started, and that's why we have it there. So there's an alternative to simulate shedding, and that's used by several people. These are just a sample of references, but Shelley, Albin, and Eldridge have used a method based on conformal mapping that works for 2D, but not for axisymmetric one. And just to illustrate that the simple algorithm that I use, whereas the conformal mapping algorithm, it really gives you identical results. There's some very minimal differences over here at later times that one can see, but the circulation, shedding, and the position of the sheet. So this is an oscillating plate in this direction. That's the problem that Jones computed, and for that problem, if I simulate his velocities, I get exactly the same results. So. Okay, so now I want to compare these vortex sheet simulation with the viscous simulation of Schneider's group. And Ava likes to work with the Brown-Michael model, so we're comparing this even simpler model of just shedding point vortices with the viscous ones. And we get overall good agreement in the position of the sheet, of the points, in both in this method less so, but there's also overall rough agreement. But if I look at the shed circulation, this is actually quite about 15%, 10 to 15% larger than there. So overall, I get good rough agreement, but my shed circulation is over-predicted by the model. This is also something that we found a long time ago in comparison with Didden's experiments, where this ring actually travels a little bit faster than that one, and the circulation that we compute is about 20% larger than the one that Didden reports. I mean, he doesn't have much accuracy in computing the circulation, but it's definitely, it's consistent with the fact that this ring travels faster. Okay, so the question is, why does the vortex sheet model overpredict the shed circulation? That's my basic starting point. So that's what brings me to this test case of this flow past a flat plate. I want to compute this flow with high resolution to better understand the viscous separation, to understand the dependence on viscosity, dependence on this parameter P, and have benchmark results to evaluate it. Now, Pullen and Perry did some experiments that I'm going to compare to later. Koumoutsakos and Shields computed this flow, but they did it at later times, and they actually didn't look at the circulation. And Ruccini and Tognacini did an interesting problem, which is a semi-infinite plate. And so you have the boundary layers of vorticity. So you have viscous flow, separation past the semi-infinite plate. Okay, so this is viscous separation past that. And because of the absence of a length scale, if you replace T you normalize it by some time T, and you replace X by T to the 2/3, and you replace the viscosity of the flow by T to the 1/3, your solution remains unchanged. So what this says is that if I compute the flow with one Reynolds number, one circulation, then if I have the time trajectory for one Reynolds number, then I really have it for all Reynolds numbers. But I do need a time trajectory. This does not imply anything on the scaling. Okay, so I cannot deduce the scaling as I could in the inviscid case from this. So I'm solving the Navier-Stokes equations. I normalize it with respect to this time. The vorticity is initially 0. The velocity is 0 on the wall, so this is my finite plate now, not the semi-infinite plate. I use a split method in time. It's fourth order. I use fourth order approximations whenever we can, and this is really based on Ling's thesis. She did a great job with this. The convection is solved using a semi-Lagrangian method. So you start out knowing your vorticity in the interior. You solve the Poisson equation, you get the stream function, you get your velocity, you convect, you get updated vorticity in the interior, and from the updated vorticity, you get boundary vorticity that cancels the other velocity component. And then you solve diffusion using Crank-Nicholson. Okay. This is what solutions look like. Under-resolved solutions are noisy like this and have some instability that starts out at the tip. And if your mesh is sufficiently fine, everything looks well resolved. She did implement this for the driven cavity problem with smooth boundary conditions and got fourth-order convergence in space. It is first-order in time because of the split method. For the impulsively started plate, which is highly singular, it's second-order in space. And first order at the tip. All right. So this is just to illustrate the highly singular flow for the impulsively started case. My vorticities below, the initial vorticities are infinite if I consider flow past this plate. And they decay like 1/t. The velocities occur over here. For later reference, the core, the vortex core, is going to have coordinates xc, yc. And omega c. Okay, these don't show up that well. I don't quite know why, but so this is just the solution in the half plane. Okay, my plate is I'm just showing it over here. Okay? So initially I have velocity going in this direction around the plate. There's my vortex sheet. So that velocity induces positive vorticity along the wall. And that vorticity actually, in the impulsively started case, immediately forms a little recirculation region. In that recirculation region, you have velocity in the opposite direction that causes negative vorticity. So this is vorticity. Blue is negative. Red is positive over here. And that negative vorticity grows. Eventually, you have this starting vortex, which becomes more clearly separated from the plate vorticity. These are passive particles I've put in the flow to see the streak lines to be able to compare with experiments. So that's this is the solution at later times. The only thing over here, it's sufficiently large times the vorticity reaches the wall and actually the axis in the middle and diffuses across the axis. Okay, this is a close-up of what happens initially. So this is at a fairly early time where you have this negative vorticity region. And this happens, again, for this impulsively started case, p equal to 0, this happens basically right away within the first 10 time steps, no matter how small delta t is. And the other thing to note is that initially you don't really have a vorticity maximum over here. The vorticity maximum is over there, and it just decays. But after some time, you get this little bump forming, and it grows, and that's when your core forms. So initially, your vortex core actually doesn't exist if you define it by the vorticity maximum. This is the dependence on time, on Reynolds number at a fixed time, and nothing, everything is over here as expected. Your boundary layers decrease. The vorticity becomes more compact. The vortex, the streak line roll-up tightens as you increase Reynolds number. And this is the scaling of some quantities that actually scale extremely nicely. So this, for example, is the y component. So what this is a solution for all Reynolds numbers and for all discretizations we use. So there's probably like 20 or 25 runs in here. And they all collapse onto one curve. And that curve is identical to the inviscid scaling behavior predicted by the similarity theory. The same is true for the x component. Initially, it scales the way it should. The vorticity core actually scales very well as a function of t over Reynolds number, and this is not predicted by anything that I know of, and I don't have an explanation for that. But it scales over like how many decades is this? 5 to 6 decades. So that's one thing that we've done is we've looked at a large range of time scales, and we see very clear scaling for several of these quantities. So the question of interest is the circulation. So I'm going to define the region omega at small times. It's not clear what is separated vorticity and what is attached vorticity. So we chose everything to the right of the tip is separated. Everything above the negative vorticity at the wall is separated. I didn't want to include wall vorticity. And everything to the right of this slant line, which is where these regions of high curvature lie, and they happen to lie on precisely a line. So that's how we define our region omega, and circulation is the integral of vorticity in that region. But I also want to look at circulation shedding rates because I want to understand the effect of viscosity on the circulation. So I'm going to define d gamma plus is actually what I'm computing with my vortex sheet model, is the amount of vorticity flux through this line. D gamma minus, well, you could think, well, that maybe is also what I'm computing with this with the u minus squared term up here. But then I have diffusion of vorticity out of here and out of here. So this is d gamma plus, this is d gamma minus, this is d gamma 0, and this is d gamma s for slant. Okay, and at later times, I have an equivalent definition as a continuous transition from this early time to a later time. And then not only do I want to look at fluxes through different portions of the boundary, but I want to look at fluxes. So if I look at d gamma dt, this is the flux that we get through the convective term. This is the corresponding term that we get from diffusion. And this is the one that we get when the boundary moves, which only applies really to this part back here. So I have 3 different components of the circulation around each one of these boundaries, and I want to look at each of them to understand what happens. So this is the total shed circulation, and it agrees with the similarity theory very well for Reynolds number 500. So Now this plot shows you the dashed line is the same data that I just showed you in the previous slide on the log-log scale. The d gamma plus the convection term, the convection of vorticity through here, that's that solid line. There is a definite gap between there. So d gamma plus, there is definitely more vorticity coming into here than you actually end up with in the vortex. The rest, the difference between the plus and the minus is lost because of viscosity. And that's what this other plot shows over here. So this red curve is the loss of viscosity through up here and through this little portion of the boundary near the tip. Okay? So viscosity is actually, yes.
In simulations, you do basically equation for the vorticity, correct?
Yes.
Because they have viscosity, what on the boundary? What kind of boundary condition?
On my computational boundary, yes. I mean outside I compute stream function. On the plate, velocity 0, stream function is 0. And I use the Thomas formula to get the boundary vorticity from the interior stream function, and we do that to fourth order. That's something Wayne and E used with E and Liu. They introduced, I mean, they've used that method. A method that has been used before, but we got it from their papers. And for the driven cavity problem, we do exactly what they do for the driven cavity, yes. Well, it's impossibly stopped. I would say it's starting. It's not stopping. Well, I'm in a reference frame of the plate, so I move the background velocity. So the background velocity starts impulsively, which is the same as moving the plate down. But I'm in a reference frame of the plate being 0, so my velocity is 0 on the plate. Okay, so this difference over here is due to viscosity. So the effect of viscosity is actually quite significant at all times. This goes down to 10 minus 4. So now I want to look at the effect of Reynolds number. Okay, so the circulation depends significantly on viscosity at all times. This is the dependence on Reynolds number. Let's ignore this first one. This is the loss of circulation due to viscosity along the axis, which is tiny at the times I'm considering. But it gives you the legend for the curves. Okay, red is Reynolds number 2000, light blue is Reynolds number 500. So this component, the convection through the bottom over here of my tip, that one is basically independent of, I mean, it's very clearly independent of Reynolds number. Okay? This component, which is the viscous component, I have a hard time resolving it for the larger Reynolds number. But it's very clear from the first 3 of these, this does not depend much on Reynolds number. So this component is large, but this does not depend much on Reynolds number. Circulation depends little on Reynolds number at early times. All right. So this is a plot of the circulation. And its dependence on Reynolds number on a linear scale for all the times we computed. And we see at the end there is some dependence on Reynolds number. Circulation increases as Reynolds number increases. So the conclusion from this is that at early times, the circulation is basically Reynolds number independent, but viscosity is largely significant. And at the final time, there is a 5% increase in the Reynolds number increases. Okay, so how do you make sense of that viscosity is significant, but the result is independent of viscosity? If I look at my d gamma dt, if I look at this red term, which is the one that accounts for viscosity, for viscous diffusion out of the vortex, I have a gradient of vorticity divided by a Reynolds number. As Reynolds number increases, the gradients increase and the Reynolds number increase, so that the overall combined effect is basically not changing. That's what this is saying. Okay? That's how I explain those results. All right. So here's a comparison with vortex sheets. The top is my streaklines computed numerically. At a fixed time, t equals 1. Didn't write that down. It's a fixed time with increasing Reynolds number. Down here is computed with the vortex sheet model. At the same time, with decreasing values of delta. I can't really claim that I want to compare the limits, because in the limit, as Reynolds number goes to infinity, the flow becomes turbulent, and the limit as delta goes to 0, I don't know what happens. But I want to say that if delta is sufficiently small, Reynolds number is sufficiently large, I mean, they roughly approximate each other. There are some differences that you see in the shape of this, but overall, I mean, good agreement to the eye. This is a comparison of the circulation over this time period. This is the plot we already saw for the Navier-Stokes solution. This is the Vortex Sheet model with decreasing deltas. And if I look at this close-up, as delta decreases, the circulation goes down. As Reynolds number increases, the circulation goes up. And this final time actually is almost identical. And I didn't choose this time to make it look like this. I mean, this was really looked very good. And we'll see there is a little bit of a difference over here. We'll see that in a little bit. The delta is my regularizing parameter, yes. Okay, so now I want to, okay. So then I say, well, I mean, I get perfect agreement, so that doesn't explain the discrepancy that I see with the experiment or with the simulations. So, but in the experiment and simulation, I actually have accelerating flow. I don't have impulsively started flow. So I want to look at the effect of this parameter P. So now I'm going to fix Reynolds number, vary P. This is the evolution with fixed P. And the one thing that actually is very different than for accelerated flow as opposed to impulsively started flow is that initially you have a time when you just have a blob of vorticity without any separation. And that does not happen in the impulsively started case. So that's interesting. This is the solution. This is the vorticities, streaklines, streamlines for increasing values of this parameter P at a fixed plate displacement, which is the appropriate quantity to look at over here as opposed to time. This is a comparison with Poland's experiment. I'm just going to skip over this since I want to get to the interesting stuff. This is the time interval in which I have no separation. And Lucchini and Tognacini, for this problem, they mention 4 stages that they don't really ever, in their introduction, they never refer to them again. But we can actually identify these 4 different stages alluded to in Lucchini and Tognacini. So this they refer to as a Rayleigh stage, where there's basically just a viscous boundary layer of constant thickness around the plate. Then I have a separation where the flow is not yet self-similar, but it's starting to be self-similar. They call that the viscous stage. Then they have a self-similar growth stage and a vortex expulsion stage. So I'm interested in this one because I didn't see that for p equal to 0. And I look at the time of this so-called Rayleigh stage, TR, and it actually, as a function of p, it scales very, surprisingly well, like p to the 5 halves, which is consistent with our results for p equal to 0. So this thing grows in time, which may account for a delay in the separation that is consistent with what we're seeing in the comparison with experiment. So here's a comparison of the vortex sheet, the streaklines at a fixed displacement for all p, Reynolds number 500, and fixed delta at 0.1. And I sort of capture the shape, the change in the shape as a function of the streakline, as a function of p. Now, as Reynolds number increases, you get more roll-up. I sort of capture it, but it's not clear. I could imagine if I increase Reynolds number, I get something that looks a little bit more like that over here. Anyway, so that's my... This is a comparison of the circulation for all p for fixed Reynolds number and fixed smoothing parameter. And it actually, here is the case I was looking at before, where I got this very good agreement at time 5. And you see that there is a 5% actually difference across here. And as I increase, if I were to increase Reynolds number and decrease the delta, this gap would actually go down. I don't know how far down, and we still have to compute these varying Reynolds number computations because they're expensive. So for a model that is so easy to compute and is so much more quicker than doing the full simulation, this is surprisingly good agreement, I find. So there's approximately a 5% difference everywhere over here. And again, as I increase Reynolds number and decrease delta further, I would expect closer agreement. So that's what this says over here. I have differences about 5% expected to decrease as Reynolds number increases and delta decreases. So my summary is I have vortex sheet simulations and point vortex models that overestimate the shed circulation. I have a test case. And I discover new scaling laws. I look at circulation over several decades. The effect of viscosity is significant, but largely dependent on the Reynolds number. I have this Rayleigh stage that seems to scale this way. And viscous circulation is in surprising agreement with the vortex sheet simulation. I should have said it the other way around. The vortex sheet simulation are in surprising agreement with the viscous simulation. So the only thing that this doesn't explain, these 5% difference does not explain the 15% difference that I was seeing with the experiment and with the difference between the experiment, the axisymmetric experiment, and the planar comparison with the Navier-Stokes. So there are a couple other things that are going on that are causing that difference, and we're doing some simulations in the 2D case to understand what they could possibly be. I think in the axisymmetric case, there are yet some other reasons that could be causing the difference, but we still have to look at the axisymmetric case closer. So this is it. Thank you.
Questions?